Okay, we're going to be looking at displacement time graphs and multi-stage problems. So let's think about how this would work. So a displacement time graph you'd have on your y-axis the displacement in meters, and then on your x-axis you have time in seconds. And let's think about a scenario. Let's think about a girl who is meeting a friend, meeting a friend 1 kilometre, 1 kilometre per metre, so that's going to be 1,000 metres down a road. Okay, now she starts off and she goes to catch the bus. She walks for 20 seconds to the bus stop, and this is 30 metres from her house. She has to wait another 30 seconds, so a total of 50 seconds for the bus. This bit's flat. Then the bus comes and takes her past the place where she's going to be meeting her friend. So she goes 1,020 metres in total away from her house. Now, as you can see, this bus journey takes 200 seconds. Now, the bus accelerates, then it goes at a constant speed, and then it decelerates when it comes to the stop. But then she has to walk back to where her friend is, the kilometre away, and that takes her 15 seconds. So we can see from this graph the motion of her journey. We see her walking at a steady velocity. The gradient of the graph gives us the velocity. So as you see here, the gradient is meant to be a straight line. Our velocity is constant, so it's a straight line. Here, she's not moving at all, so it's flat. Her displacement doesn't change, she's at rest. Here, the curve accelerates, then a constant velocity, then decelerates. Now here it goes down. This shows a negative displacement because she's walking back in the direction that she's come from the 1,200 to the 1,000 metres away from her original starting point. When we're sketching the graph, it's really important to show clearly the shape of the graph, to show clearly when you've got a straight line, when there's no velocity, when the person's at rest, or when there's acceleration or deceleration. So we're going to try an example to see how this would work. So, a racing car passes the finish line of a race moving at a constant velocity of 60 metres per second. After 5 seconds, it starts to decelerate. At 3 meters per second squared until coming to rest. So we're going to sketch the displacement time graph for the motion after the end of the race, measuring the displacement from the finishing line. So let's T1 be the time from the start of the first stage, and T2 the time of the second stage. So what do we mean by the first and second stages? So here is our racing car at the finishing line, and for T1 the velocity is at constant 60 meters per second. Then here we see a deceleration for T2 seconds until it goes from 0. So the velocity, the initial velocity here will be 60 and the final velocity will be 0. And the acceleration is 3 meters per second. So we can work out, and this is 5 seconds. So we can work out the distance here. We can work out S equals VT. So that's going to be 60 times 5, which is 300 meters. So for 0 less than t less than 5, S equals 300 or 60 t, where t was 5. So I'm going to do the wee sketch up here to put everything that we've got on down. So we've got our S, we've got our T, and always put the units that you're working on your graph. And we've got a straight line of constant speed for 5 seconds, and this is 300. Now for the second stage, we're going to use V equals U plus AT. And we'll use this so we can find the time. So we know the final speed is 0, we know the initial speed is 60, we know the deceleration is 3, and then we've got the time. So rearranging that, we will get T2 equals 20 seconds. Now we can use V squared equals U squared plus 2AS to find the displacement. So it'll be 0 equals 60 squared plus 2 times 3 times S. S2 is going to be 600 if we rearrange it meters. Now, the total time equals T1 plus T2, and the total displacement equals S1 plus S2. So that is, the time is 5 plus 20 equals 25 seconds, and the total displacement is 300 plus 600 equals 900 meters. Now we can do this. So here it goes to 900 meters and the time is 25. Now we can use our equations of motion to give us an equation that explains the curve. So we have S equals ut plus a half a t squared. Now if we were to do it for S2, that's 60 times T2 plus a half times minus 3 T2 squared, which is 60 T2 minus 3 over 2 T2 squared. And for S2, for S1, for the beginning piece of the motion, we'd have for the total distance here. So this is for the displacement for the whole thing. We can take S1 plus S2, which we've just worked out as this. So, and S1 is 300 plus 60 T2 minus 3 over 2 T2 squared. Now if we, for T2 equals T minus 5, and what we've got up here. So we can say that is 300, S equals 300 plus 60 T minus 5 minus 3 over 2 T minus 5 squared. If you open the brackets and rearrange everything, you'll get S equals minus 3 over 2 T squared plus 75T minus 75 over 2. We're going to do another example. This time we've got a cyclist. And he travels at a velocity 15 meters per second when he passes a junction. He then decelerates at a rate of 0.6 meters per second squared until he comes to rest. A second cyclist travels at a constant velocity of 20 meters per second and passes the junction 4 seconds after the first cyclist. Find the time at which the second cyclist passes the first, and the displacement from the junction when this happens. So let T1 be the time cyclist 1 reaching the junction, and let T2 the time the second cyclist reaches the junction. Let S1 be the displacement of cyclist 1 from the junction, and S2 be the displacement of cyclist 2 from the junction. Okay, so we're going to be using this S equals ut plus a half at squared for the displacement. So for S1 it's going to be 15 T1 plus a half times minus 0.6 T1 squared. And for the second cyclist, now the first cyclist is decelerating, the second cyclist isn't. So it's going to be the S equals Vt. So S2 is going to be 20 because it's going at 20 meters per second, and it's going to be T2. Now T2 is going to be T1 minus 4. So we can put this into here, 20 T1 minus 4. we want to know the distance when the cyclists pass. So at that point, the two displacements from the junction are going to be the same. I should run a wee diagram. You've got this junction, and you've got cyclist 1, this distance, and you've got this other cyclist behind. Coming, this guy's slowing down, this one's going at a constant speed, and so this distance, when this distance here is when S1 equals S2, this distance from the junction. So we can make, by equating the two together, we will have 15 T1 minus 0.3 T1 squared equal to 20 T1 minus 4. So we just sorted all that out and equated the two. So we can now solve, well, let's make this into a proper quadratic equation. So we'll just break up the brackets, simplify it down, gather terms, and we'll get that. And now we can solve the quadratic equation. 3t1 plus 80, t1 minus 10. So that's going to give us a negative. It's not going to be negative time because that can't happen. So t1 must be 10 seconds. So S1, if you slot t1 back in, S1 must be 120 meters, and so must S2. Now, I'm going to do another cyclist one. Cyclist A is travelling at 16 meters per second when she sees cyclist B 15 meters ahead. Travelling at a constant velocity of 10 meters per second. Then cyclist A slows at a rate of 1.5 meters per second squared. Find the minimum gap between them. So we've got the initial position. Of cyclist A and cyclist B. So this is A, this is B, and A is travelling at 16 meters per second, and cyclist B is 15 meters ahead, travelling at 10 meters per second. So cyclist A is going faster than B. So even though cyclist A starts to slow down, for some period of time, her velocity is still going to be greater than cyclist B. So the gap is going to get shortened. So at some period, let me get a unicycle. There's going to be some gap which is smaller. So during that time, cyclist So there'll be a distance S1 that cyclist A travels. This is still A and this is still B. And then there'll be some distance here that cyclist B has travelled. I'm going to change those numbers around. So this is distance 1, the distance that cyclist B has went, and this is distance 2, the distance that cyclist A has went. And this has all happened at some time. The time that this has happened is the same, time t. So the time t is from when they're 15 metres apart to when they are at their minimum distance. So we're going to have the gap g. The gap t is going to be the gap at time 0 plus these two distances, S1 minus S2. So this gap here, you've got like 15 plus S1, but then minus S2 will give you this gap here. Here. So we know the initial gap is 15. And the distance for this one, cyclist B is going to be VT because their rate isn't changing. So it's going to be their velocity, which is 10 times t. But the S2 is going to be equal to ut plus a half a t squared, which is, their initial is 16 t plus a half times 1.5 t squared, which will be, we'll put it in here minus, and then we'll have your 16 t minus 0.75 t squared. Now we can break open those brackets, so we go 15 plus 10t minus 16t, minus and a minus makes a positive 0.75 t squared. We're going to gather terms, and then we're going to complete the square to get 0.75 t minus 4 squared plus 3. The minimum gap, therefore, is 3 meters at 4 seconds, because this gives us the minimum and this tells us when that is at the midpoint. Yeah. So I hope that helps.